And today I'm going to start on a very interesting topic and also a very important one, which is on radiation. Okay, on radiation by electromagnetic sources. Without radiation, we cannot have a lot of things that we have nowadays, which is wireless communication. Every one of us carries a cell phone. Our cell phone is actually talking to another cell phone through base station antenna towers and so on. And some of them are actually connected by satellites, low Earth orbit satellites, and so on. So without this physics, we would not have all the conveniences that we have, that we are living with now. We find that wireless communication is so important. So I'll go through a brief history of radiation by a Hertzian dipole, and then talk about some approximations, near field, far field, radiation power directive, gain pattern, and radiation resistance. Okay. So here is a antenna tower. This antenna tower is coming from this station AM 920. And the frequency of this is 920 kilohertz. Okay. And the wavelength, I believe, is around 300 meters at this frequency. There's a simple rule of thumb that I used as a student when I was working in a microwave lab. I was always told this rule of thumb, 10 gigahertz. 10 gigahertz implies 3 centimeters, okay? Then 10 gigahertz is 10 to the 10 hertz. The wavelength is 3 centimeters. And then if you look at this station, is about 1 megahertz. Okay, 1 megahertz is 10 to the 6 hertz. So if you can compare these two frequencies, one of them is 10,000 times higher than the other frequency. Hence, if you go to 1 megahertz, then the wavelength should be 10,000 times longer. So you have 30,000 centimeters, and then it would be 300 meters. Okay, you can use this formula as a rule of thumb to work out wavelengths. You just have to remember one bit, which is this one, just using proportionality constants and scaling of wavelengths and so on to get wavelengths at one frequency. And then you can quickly figure things out. Okay, so Hertzian dipole is going to be what we want to talk about, because when you have a wavelength that is so long, a dipole, even though it's an antenna tower, which is not small, can be thought of as a short dipole. So this is a short dipole, which is approximately what we call a Hertzian dipole. Okay, it is approximately a Hertzian dipole because it is so much smaller than the wavelength that it is operating with. Okay, and Hertzian dipole was invented around 1888 or Heinrich. I think his name is Heinrich Hertz. Okay, he did an experiment in 1888 and proved that you can use a small dipole to radiate electromagnetic field. And you can imagine how slow progress things were. 1865 was the onset of Maxwell's equations. Okay, and then it was some 23 years later, if you subtract these two, it's 23 years later that people understood Maxwell's equations, what it was all about, and then started to work on experiments to verify Maxwell's equations. And the story was that when Maxwell's equations were first written down, very few people can read beyond the first 50 pages of treatise of electricity and magnetism. So James Clerk Maxwell wrote a book called The Treatise of Electricity and Magnetism. It was very hard to read. Okay, it was not until Oliver Heaviside, in English, an eccentric English genius, as some people like to refer to as, who took Maxwell's equations, which were some 20 of them, and rewrote them in the 4 Maxwell's equations that we see in textbooks these days. Okay, so knowledge progresses slowly throughout the ages. This is what we can learn from this historical story. But when a dipole is very short compared to wavelengths, we can approximate it with a dipole such as this one. It can be thought of as consisting of 2 reservoirs at the end, okay, 2 charge reservoirs at 2 ends, and then you drive it with a generator. And at very low frequency, it's almost like if you have a transmission line, and if you connect it to a generator, you probably would know that how difficult it is to drive current into this transmission line because it is an open circuit. So one way to drive current into this transmission line is to put a capacitor at the end of this open circuit transmission line. If the capacitor is large, then you can have a current flow. Okay, you can have a current flow, AC current flow through this transmission line. The same idea is being applied by Hertz. What he did was that he used a sphere which is large enough so that there is a capacitive coupling. There is electric field that goes from this sphere to the other fields. So you can think of them as having capacitive coupling between them. And because they have capacitive coupling, you can think of the equivalent circuit as something like this. Okay. So how did he drive this antenna? Well, he made 2 spheres which are relatively large compared to the size of the wire. His driving point was here. Okay, he knows that he needs large capacitive coupling between these 2 spheres in order to drive any currents into this antenna. And whenever you have some current traveling in the antenna, you can show later on by mathematics that this current, which is traveling back and forth, would radiate. And that is how Hertz did it. And this is how he drove his capacitors. He actually used a transformer and he used a battery to charge up the high voltage, and then he used a switch. And when you have a switch, you can cause a large voltage transfer by this transformer to set up the voltage, and this voltage drives the current into the capacitor. And he picked up the signal using a loop antenna, a current loop. The current loop will intercept the magnetic field generated by this antenna, and the magnetic field produces a force by Faraday's law or Lenz's law, produces a voltage at this gap, and he actually can detect electric sparking, the sparking of electric field at the voltage gap, indicating that, in fact, his receiver is picking up some electromagnetic signals.